Welcome back. Now we are going to look at what are the different applications that we can think about and how we can use this wonderful method of Monte Carlo simulation with the Metropolis algorithm. So, just to revise quickly again, we have 4 steps here for a particle in a space x and y. We just take 2 random number generators in x and y, and I am only looking at 2 dimensional model. You can also have 3 x, y and z and 3 dimensional model, and you can have 3 random number generators. But the important thing here, because it is random number generator, it has to have good random numbers, and that is not an easy task. You may think that, oh, I can generate random numbers, not a problem. But what happens after a while, those random numbers start repeating themselves. So, you do not have good quality of random numbers generated, and that are created by expansion of the pi. So, a lot of this effort is created, and there are lots of these algorithms out there to seed good random number generators or good random numbers. Once you have collection of these random numbers, let us say million of those, you can pick them between -1 and 1 and then add to x, y and z, and then create new configuration of a particular atomic structure. So, I can take H2O water atoms, water molecules, and then I can change the position of oxygen and hydrogen using as a triplet, because it is a molecule, there is a bonded interaction there between 2 hydrogen atoms and 1 oxygen atom. And with that molecule, I can move these molecules randomly and their positions and then calculate. So, for that then I use Metropolis Monte Carlo procedure, where it says that calculate delta u between initial and the final configuration, and then find the difference, and at every time you take the difference, you do 2 things. You look at the value, is it less than 0, if it is less than 0, then accept the move, and if it is greater than 0, then you can still accept only if the distribution is allowed by the Boltzmann factor. So, the Boltzmann factor, which is exponential of minus beta delta u, has to be greater than those random numbers that you have generated in order for you to accept that particular move. And so, with that understanding, we know that we do not have to calculate the equation of motion. So, if you look at the application of Metropolis Monte Carlo method is quite a bit. If you look at phenomena of different kinds of physical situation, or even numerical evaluation of multidimensional integrals or multidimensional energy space, then Monte Carlo makes sense, because there are a lot of unknowns in terms of the Newton's equation of motion, but I can even look at some of the electronic properties and do Monte Carlo simulations there. So, if you look at simulation of random walk process, which follows the Markovian chain model in statistical mechanics and condensed matter physics, that is an important application. Especially particles and radiation transport. So, when you have radiation, let us say radioactive radiation hitting a particular material, and it is knocking off some of the particle inside that material, because the neutrons are bombarded on particular material, that is where you do the particle and random transport simulation, and that is where the application in nuclear energy and nuclear applications comes into handy, and that is where we use Monte Carlo, Metropolis Monte Carlo simulation. As you know, its origin is related with some of those kinds of calculation done in 1950s. Now, if you look at where molecular dynamics uses it, one is that as you remember from our various VMDL simulations, that it takes long time for system to come to equilibrium. So, why not I just use Monte Carlo as the initial point, take the particles, move them around, get to the 0 minimum energy configuration, and use those configuration as the initial point for the molecular dynamics. So, now I saved lot of time in those calculations where I was trying to get to equilibrium. So, for us to go to the equilibrium configuration, all I have to do is use a very simple random number generator, give the original position of the particles, and then do 1,000,000 of those configuration, and then using Metropolis algorithm accept some of the configuration and get to the minimum energy. That is where we find the equilibrium configuration. So, that is where some of the methods like simulated annealing algorithm for optimization of multidimensional energy space. This is very big application, because in simulated annealing essentially what you do, you heat a particular material just like you do in annealing of the material and quench them. So, what happens that once you take them in a very randomized situation with particles at high temperature, and if I quench them very quickly, then they will get to a random, or what we call is disordered phase, glassy phase, or amorphous phase. So, those amorphous configurations can be some of the very important configuration where you can find that minima in the potential energy function. And so, simulated annealing allows you to go to that, and that is also used in some of the tight binding theories, which we will look at in the sections coming up, where we talk about the various potential energy function and higher level methods which connect you to the quantum mechanical calculation. So, finally, the MC can also be used to study dynamic variable by using kinetic Monte Carlo method. So, there is also a way to look at the kinetics of it, not as convenient as molecular dynamics, because in molecular dynamics we are keeping all the information, but with kinetic Monte Carlo, where you essentially are now looking at the succession of equilibrium configuration in time. But again, for every equilibrium position in the state space, I have to get to that equilibrium primarily because of ergodic theorem, and I can then apply that ergodic theorem and then look at succession of those equilibrium snapshots and construct a trajectory in some shape or form. And so, I can get back some dynamic information, but in a non-deterministic or what I call stochastic way. So, it is possible. So, Monte Carlo does open up another model of learning and understanding. So, now let me show you a VMDL, our favorite tool for understanding some of these behaviors. So, I am going to show you Brownian motion, which is given in your VMDL. So, let me open up VMDL here. Okay, now let me stop it first, and then I am going to make it bigger so that you can see it. Okay, so now we have this. So, we are first looking at the atoms. Let me move it. Okay, this should be good. All right. So, now we are looking at this atom, and it is now using random number generators to create some of Brownian motion, as they call, which is the random walk. So, if you look at this walk, you can see that the system is, and we are looking at temperature versus time graph. So, we are looking at the water molecule here and how it is changing with respect to time. And then we are also, so this is, let us say this is the water molecule, and you are looking at motion of that. So, let me start it again. From that position it is going backwards, and then let us look at any pollen, because if you look at the kinetic energy of this system, you are also looking at the randomization. So, in this case you can see that we can look at the kinetic energy and potential energy, and this is temperature versus time. So, even though we are in a random generator positions here, we are able to look at system going through different kinetic energy formations as well as potential energy. So, what we will do, we will do same thing with large number of particles, and then look at which ones are the accepted configurations. So, with this idea about random number, random walk, but looking at every step with those situations, which one is the configuration for all n atoms in 3n dimension, we are now able to utilize the Monte Carlo simulation method. So, again, this simple concept with a very I would say serious consequences, in the sense that you can do serious physics using this random number generators and with the Metropolis Monte Carlo methods. And if you look at literature, and I have supplied some of the references, you will see lots of application of different kinds now used with MC. But in our case, where our focus of this course is molecular dynamic simulation, MC provides a very important tool to get to the equilibrium configuration by not spending so much of the computation time, just by doing random selections and going to the minimum energy. And most often that is used quite a bit in conjunction with MD, especially when you have complex system. So, if you have hydrocarbon chains, which you will see one of the application that I did myself in molecular tribology, where you look at hydrocarbons on the surface of silicon and you want to find out where we can create a lubricated surfaces with what is called boundary lubrication. Then first we start with this complex system with hydrocarbon and silicon atoms, and then we make sure that they get to the equilibrium configurations using Monte Carlo simulation, and then we start our MD simulation. So, this is a very handy method, very popular method. So, I welcome you to try that in your software programs and see how it works for you for the same configuration that you may have used in Lennard-Jones functions. Thank you.